Okay, so the big topic that we're in is entropy and the second law of thermodynamics. And there's two more little subtopics. Um, um, so the two last, oh, thank you. I would have done the whole class like that. Okay, the two last topics in entropy and the second law of thermodynamics. The first one is isentropic processes. And we're only going to do this for ideal gases. So what does isentropic mean? No change in entropy. Iso means same. And the second one is, let's see, what do I call it? The second law for control volumes. Okay, so we're going to start with isentropic processes. For ideal gases. And this requires two things. So for a process to be isentropic, this is actually true for anything, not just ideal gases, but it requires that there's no heat transfer across the boundary, no heat transfer to or from the system. Can anyone tell me a way or a couple ways that things that you can be told in a problem to know that there's no heat transfer to or from the boundary besides those specific words? Insulated or isolated. Isolated is even stronger than insulated. Any other ones? This was back when we were talking about devices. I gave you a list of some things. Yep.
Is there one that's like isothermal something?
Yeah, that's different though. Something can be isothermal and still exchange heat. So for example, if you have in that Carnot engine problem, one of those processes was an isothermal expansion.
Right.
So the way that you get an isothermal expansion is you allow heat transfer into your system. The temperature just doesn't change, but it'll go from like partly liquid to all gas or whatever, So some other ways are fast travel through your system. Or the process is really fast, so there's just not time for heat transfer. Small temperature difference between the outside the boundary and inside the boundary. So I think that's all of them. But anyways, you need to have no heat transfer to or from the system. And then second, the process needs to be internally reversible. Anyone remember what internally reversible means? So inside the boundary, there are none of those things that I listed as irreversibilities. There's no friction, no uncontrolled expansion of a gas. There's 7 or something of those. So if you have these two things for an ideal gas, then we know that, so we have this expression that says delta little s for an ideal gas is equal to Cp times the natural log of temp 2 over temp 1 minus R times the natural log of P2 over P1. And we also have this one that says the change in specific entropy is equal to Cv times the natural log of T2 over T1 plus R times the natural log of specific volume 2 over specific volume 1. And if it's an isentropic process, there's no change in entropy, then these both go to 0. And so these give this new form that says Cp times the natural log of T2 over T1 is equal to R times the natural log of P2 over P1. And Cv times the natural log of T2 over T1 is equal to, so I could write this as negative of this term, just doing the algebra, or because of the way the natural log works, I could just flip those two, the numerator and denominator, that fraction, and write this as R times the natural log of V1 over V2. So these two are flipped. Okay. Now what you want to do from there, you kind of have some different options. So how are we going to use this? First, let's assume that Cp and Cv are essentially constant. So what's the assumption that we usually make if we're going to use Cp or Cv as constant? Small change in temperature. Okay. So let's start with this first one that says Cp times the natural log of T2 over T1 is equal to R times the natural log of P2 over P1. So I'll write this as natural log of P2 over P1 is equal to Cp over R times the natural log of T2 over T1. And now if I want to find that ratio of pressures, what would I do to get P2 over P1 by itself?
You would bring everything to be
Yep.
easy.
Perfect. Yep. So now we'll go E to natural log P2 over P1 is equal to E to the power of Cp over R times natural log of T2 over T1. Which says So this is just P2 over P1. And if you go through all the algebra here, you get you get e to the power of Cp over R, natural log of T2, divided by e to the Cp over R, natural log of T1. So what we get here is this is an expression for the ratio of pressures as a function of temperature. Okay. Remember that this expression here, this is fine. We can use this no matter what our temperature range is. So really, when I said this, I didn't have to assume for any of this that this is a small change in temperatures. But now if you're going to use the same value as Cp for both of these two, the numerator and the denominator, you need to assume that that's constant. But if you could look these up at the two different temperatures, then you're not making any assumptions at all. Another thing you can do is, so let me say, this is very accurate if you look up Cp at each temperature. It also gives good results using a single value of Cp if there's a small change in temperature. Last time I told you about a way that you can go to ideal gas tables for a material and look up those S super zero values. So this can also be written. So let's cross this out here. I shouldn't have written this here. So how do we use this? Let's get this guy out of here. So there's no requirement that this be a small change in temperature. There is a requirement that it's a smallish change in temperature if you're going to use the same Cp value here. But this can also be expressed as P2 over P1 is equal to e to the power of, so I'll write this in a bracket, S superscript 0 at T2 divided by R divided by e to the power of S super 0 at T1 divided by R. and you can actually look up that whole exponential in the table. It's not like it would be hard to plug that into your calculator, but you can also write this as PR of T2 over PR at T1. So S0 and P sub R can be looked up by temperature. In an ideal gas table. Okay, so you need to know, you need to have an ideal gas table for the specific gas you're working with. Like we have one for air, which is the most common ideal gas we use in calculations. But if you don't have these tables, it's not too much more effort to just do this. And this is the approach that I'm going to ask you to use on in assignments or tests or whatever, okay? You could also go starting with the other one. So we have starting with the other delta S equation, we have CV times the natural log of T2 over T1 is equal to R times the natural log of V1 over V2. So the order is switched on that side. And then I'll write this as natural log of V1 over V2 is equal to CV over R times the natural log of T2 over T1. And then raise both sides to as powers of E. So you get E to the natural log of V1 over V2 is equal to E to the power of CV over R natural log of T2 over T1. And so that gives you V1 over V2 is equal to E to the CV over R natural log of T2 divided by E to the CV over R natural log of T1. So again, what we have here is the ratio of volumes expressed as a function of temperature. And you can make, intuitive sense out of the fact that these V's are flipped compared to the P's. These equations look, the right sides of these equations look very similar. Like compare these. The only difference is the one for pressures is a CP and the ones for volumes is a CV. That makes it sort of easy to remember. But on the left side, the difference is we're talking about either the later pressure over the earlier pressure or the earlier volume over the later volume. But that makes sense if you think about if this process, if the pressure increases, the volume decreases. So they always, you'd expect them to have that sort of inverse relationship, you know.
We multiply the specific volume by mass and use it for an expression of volume versus
Yes,
volume.
exactly. Yep. Yep. Okay, so with these, remember, these are ideal gases, so you can always use all the, so notice, these are only for ideal gases. So you can also use it in any problems like this. You can use the fact that PV is equal to RT, that U is only a function of temperature, that CV is equal to du dt, and that Cp is equal to Cv plus R. Okay, that's all the ideal gas stuff that we use. All right, so let's do an example problem. So let's say this is actually a physics lab that that we do in Physics 1. Well, I don't know if people still do it. I haven't taught Calc-based Physics 1 in a few years, but so we had a lab where you have a syringe that's airtight, and you change the volumes of the air in the syringe, and you use the lab pro to measure the pressure, and you come up with a relationship between the temperature and the pressure. Anyone done a lab like that? And okay, so let's say that we have air at 22 degrees Celsius, that's room temperature, and atmospheric pressure, so 1.01 times 10 to the fifth pascals in a syringe. And then we compress the air to half its original volume. And the question is, what's the final pressure assuming? So first we'll make the assumption that that was made in that lab, which is just sort of a basic, a very basic thermodynamics lab. And we assume that the temperature stays the same. So you compress this gas, and we assume that heat transfer occurs so that this temperature stays what it was before. It just stays room temperature. Okay, so that would be an isothermal case. So that's a constant temperature. But then second, and so when we did this lab, it never came out quite the way we expected it to look. It never came out, so we always assumed it was isothermal, but the data didn't really suggest that it was isothermal. So what's really going on there is this syringe is plastic. It doesn't conduct heat very well. We're doing this experiment pretty quickly. We're not waiting an hour or anything for the temperature to come back to room temperature. And so what's really closer to happening is that we're compressing this gas, and there's no significant heat transfer. It's an adiabatic process. Okay. And inside, if you do this compression reasonably slowly, there are no internal irreversibilities. So this is internally reversible. And so what's really a better assumption to make about this is that it's an isentropic process. And so by doing the calculations, assuming an isotropic process, you actually get values that represent the data you measure a lot better. Okay, we didn't do this in the lab because we weren't talking about this kind of stuff, but so let's do it first for an isothermal case. So okay, we're assuming at instant 1, we have a temperature of 22. That's in Celsius, so that's 295 Kelvin. We have a pressure P1 of 1.01 times 10 to the 5th pascals. And I'm just going to call the volume V1 there, the specific volume. Well, I'll just call, sure, I'll call it V1. And then at instant 2, the temperature is still 295 Kelvin. The pressure P2 is what we're trying to find. And the volume V2 is half of V1. So we can just do this using the ideal gas law. We have that 1.01 times 10 to the 5th times V1 is equal to R for air, 287, times 295. And so that specific volume is 0.838. And that is meters cubed per kilogram. And now we'll do the same thing at instant 2. We have 1.01 times 10 to the 5th. No, we don't. This is what we're trying to calculate. P2 times the volume, which is 2 times this. So 1.677 is equal to, yes?
How do you get R?
That's just, since we use air all the time, I'm just using a value that we've calculated a bunch of times before. But the way you calculate that is the universal gas constant, 8.314, divided by the molar mass of air in kilograms. So how many kilograms a mole of air is. And you have to do that as 80% nitrogen, 20% oxygen. But that's the number that you get. You can definitely find that at least once in notes. Okay, so this is equal to 287 times the temperature. Yes?
The volume is 2 multiplied by 0.838.
Yeah, but then there was, I rounded off and now I rounded off again. So that's why it looks like it.
It's the specific volume, right? So if the
No, you are right. You are right. Thank you. So P2 times 0.5. Yes, that's very important. So 0.419 is equal to 287 times 295. And so P2 is equal to 2.02 times 10 to the fifth pascals. Okay. Well, you can see how that relationship works. It's just a simple inverse relationship because the stuff on the right side of those equations isn't going to change. So if you double one of the things on the left, you have to cut the other thing on the left in half, right?
Assume that in isothermal situation that they're directly related to one another, or just that P, well, in my chemistry class was basically like PV equals PV2 or something.
Well, so I mean they're inversely related in a yeah. So for an ideal gas in an isothermal process, P2 over P1 is equal to V1 over V2. Okay, so now we're going to go to, this was part A, now we're going to go to isentropic. And we have these two relationships. I'm going to use these two boxed relationships. So P2 over P1 is equal to, this was E to the power of Cp over R times the natural log of T2 divided by E to the power of Cv over R times the natural log of T1. This should have been a Cp also. At around 22 degrees Celsius, Cp is about equal to 1.005 times 10 to the third. This is in SI units. And R,
What is the SI unit for CP?
let's see. So CP is CP is the HD temperature for SI units, and so that is joules per Kelvin. And this is no specific. So
Joules per kilogram per Kelvin.
right.
Thanks.
Mm-hmm.
I don't provide my answer, but I do kilojoules, but I guess it's still the same as long as you provide the units in the answer.
Yeah. And R is equal to 287. That's in SI units. And so now instead we have to go to the second equation that says V1 over V2 is equal to E to the power of CV over R times the natural log of T2 divided by E to the power of CV over R times the natural log of T1. And now, so we know what the ratio of the volumes, well, so we can do it in two steps. We know that CV is equal to, remember CP is equal to CV plus R. So CV is equal to CP minus R. So that is 1.005 times 10 to the third minus 287. So that's 718 joules per kilogram Kelvin. And so now V1 over V2 I guess what we'd really want to do here is, so let's go back to, this expression. Natural log of V1 over V2 is equal to this thing. And I will multiply both sides by R over CV. So we have R over CV times the natural log of V1 over V2 is equal to the natural log of T2 over T1. And now we'll take both sides as powers of E. So we have, so E to the natural log T2 over T1 is equal to E to the power of R over CV natural log V1 over V2. And so T2 over T1 is equal to E to the power of R over CV. Well, I'm just going to use this expression. So E to the power of R over CV times the natural log of V1 over V2. And we can plug all this stuff in. So R is 287, CV is 718, so that's 389 Kelvin. Okay, so that's the temperature. And now we can go back to this expression for the pressures. So P2 over P1 is equal to E to the power of CP over R times the natural log of T2 over T1 2.637. So P2 is equal to 2.637 times the starting pressure so 2.66 times 10 to the fifth pascals. Any questions about that? I made it look a little harder than it is, but just remember what you have is you have relationships in the case of an isentropic process for an ideal gas. You have relationships between the pressure ratio and the temperature ratio, or you have a relationship between the volume ratio and the temperature ratio. And so the rest of it is just algebra, getting there. Okay, so the next thing we're going to do, and we can't get into much of this today, but I can introduce it. So the last topic in the second law of thermodynamics is the second law for control volumes. And it's going to come from the fact, so we've seen this before. So the change in entropy is equal to the integral of all the heat transfers divided by the temperatures where they're transferred around the boundary plus some sigma. So this sigma is called the entropy produced. And this integral, is that for an actual process or an ideal process? Well, think first of the definition of entropy. The definition of entropy is this integral for an ideal process. Okay? So if this was an ideal process, that sigma would be 0. Okay? There would be 0 entropy produced by that process. This is the actual process, and so, presumably this is going to give you a value a little bit smaller than an ideal process, and that's going to produce some entropy. That's going to cause some inefficiency. Remember that entropy produced is like a measure of inefficiency. And just like we always have done with control volumes, we're going to write this in terms of rates. So if you rewrite this in like a rate form, you get something that says the time derivative of entropy with respect to time is equal to the sum of all the rates of heat transfer divided by the temperature where it happens, all the way around the boundary, plus a rate of entropy production. And now, just like just like we did with the control volume version of the first law of thermodynamics. We considered what's happening inside the control volume, and then we considered, in that case, it was the energy that's being carried in at the inlet and the energy that's being carried out at the exit. In this case, it's the same, but we're just going to think about the entropy carried in at the inlet and the entropy carried out at the exit. And so the form that we're going to get is ds dt for the control volume is equal to the sum of all the rates of heat transfer around the boundary plus the rate of mass flow at the inlet times the specific entropy at the inlet minus the mass flow rate at the exit times the specific entropy at the exit plus sigma dot. This sigma dot is the rate of entropy production. And remember, sigma has to be greater than or equal to 0. And sigma dot also has to be greater than or equal to 0. So this is the equation that we're going to use.
Is that Q dot or like the whole thing dot?
Q dot only. Okay, well, we'll get back into this next time, but you can, if you want to take a minute to think about that later, you could figure out why these are the terms. But, it's really a simpler looking equation than the first law was, because there's no, that entropy isn't made up of a bunch of different things. It's just the entropy.
What happens if there's multiple inlets and exits?
Yeah, then you just add on multiple terms for all of them. Yes?
The S, what does it stand for?
The capital S?
Yes.
That's the extensive entropy. So as opposed to the specific entropy, which is capital S divided by M.